right, so this is our continuing reading of Simondon's Individuation in the Light of Notions of Form and Information. We're starting at page 62 of the translation. We're in chapter 2. Okay, so yeah, last time we started the chapter. We had the examples of the pendulum systems, the different types of pendulum, and the way that potential energy is present in those systems. And so one of the key points that he made in that part that we read last week is that potential energy is always relative to a system, in the sense that it has to do with the possible transformations of a system, but it doesn't mean that it's not real, that it's something that's only an artifact of our knowledge of the system or something like that. So potential energy is a real property of a system. It doesn't depend on us as observers, but it's always relative to a particular system. Yeah, so that was sort of the key point of that first bit that we read last week. And we'll see more about potential energy and how it relates to the structuring of a system as we continue reading today. So I'll get started. Yet, if we consider the exchanges of energy implicated in state changes like melting, vaporization, and crystallization, we will notice the appearance of particular cases of irreversibility bound to the changes of the system structure. When looking closely at a crystalline structure, for example, we can clearly see how the ancient notion of the elements has to give way to a theory that is both structural and energetic. The continuity of liquid and gaseous states allows us to unify these two states in the shared domain of fluid in the homogeneous state. By contrast, this domain of the homogeneous state is clearly separate due to the frontier constituted by the curve of saturation from non-homogeneous states. And there we have our diagrams, which I'll come back to in a minute. Between the crystalline and amorphous states, there is an evident discontinuity that we can liken to what exists between an energy of the macroscopic order and an equal energy in absolute value, but of the microscopic order, like the thermal energy in which the aforementioned example has been able to degrade during an irreversible transformation. Indeed, according to Tammen's hypothesis, the crystalline state would be characterized by the existence of privileged directions in crystallized substances. The properties of these substances present different values following the direction in question. Such are the properties clarified by the study of the geometrical form of crystals and the various manifestations of crystalline anisotropy. The amorphous state, on the contrary, which includes gaseous, liquid, or vitreous amorphous solid states, is characterized by the absence of privileged directions. The properties of amorphous substances present values that do not depend on the considered direction. A body in the amorphous state does not possess a determined geometrical form and is isotropic. Only an external action, such as a non-uniform pressure, a pulling, a twisting, or the existence of an electrical or magnetic field, can render a body amorphous. That should be can render an amorphous body, is what that should be. Particularly a vitreous, temporarily anisotropic body. If an amorphous body is represented as a body in which the constitutive particles are arranged in a disorganized way, we can suppose that the crystal, on the contrary, is a body in which the elementary particles, atoms or groups of atoms, are arranged according to organized distributions called crystalline networks. Bravais acknowledges a distribution of the various elements or chemical groups of a crystal in terms of a system in which each point represents the center of gravity of these various elements or chemical groups. This simplified expression supposes the element or chemical group to be immobile. If it is animated by a vibration, the regular point represents the average position around which the element vibrates. This is its position of equilibrium. All these systems of regular points can be obtained by the juxtaposition of parallelepipedic networks containing nothing but elements or chemical groups of the same nature that are ranked according to their symmetries in the 32 classical groups of crystals. The crystal's anisotropy is understood in this way, for these networks can be divided into systems of planes passing through the various regular points of the network in question, insofar as each system is constituted by a set of planes that are parallel with and equidistant to one another. These systems of planes correspond to privileged directions along which the crystal's limitative surfaces can be arranged. Accepting Bravais' theory, Tammen completes this representation of the differences between the states of matter by assimilating the amorphous solids with liquids that are endowed with a large amount of viscosity and rigidity. This reveals that there is a veritable continuity between the solid and liquid states of a vitreous body. For example, at the normal temperature of its usage, glass presents an exceptional rigidity, When the glass blower raises the temperature, both the rigidity and the viscosity of the glass progressively diminishes until at a very high temperature, what remains is a veritable liquid. I'll stop here because this is, again, a big, long, multi-page paragraph. So let's go back a little bit and go over some of these diagrams. So you should be able to see my screen showing the diagram, or you can look on your own PDF. So the first one, labeled Figure 5, is the one to look at. So what this shows, so we have temperature along the x-axis and pressure along the y-axis, and then we have the different curves of transformations of phase of matter along those two dimensions of temperature and pressure. So we have so there are multiple states that the substance can be in. It doesn't mention what substance in particular this is, but it's sort of an example substance, I suppose. So in the bottom right-hand corner, we have the gaseous state. Above that, we have the liquid state. And then to the left, we have the crystalline state. And then along the bottom left, we have the vitreous state. The difference between the crystalline and the vitreous state is the important one here, or one of the key ones here, because these are two different forms of solid. So in a crystalline solid, you have a regular repeated structure. Coulomb is curve. So you have a regular repeated structure in a crystalline state, meaning that it's anisotropic. So in certain directions, you have so that there's a privileged direction to the substance. So some if you proceed at a certain angle, then you get a repeating structure. But if you proceed at a different angle, then you don't get that same repeating structure. So it's the substance is not the same in all directions. There are privileged directions within the mass of the substance. So that's the crystalline state. And then the vitreous state is an amorphous solid. So it's isotropic, meaning that it has the same structure in all directions. There's no privileged directions within the mass of the substance. And the name vitreous suggests glass as an example. So glass has a vitreous structure. So it's not crystalline in that sense. It doesn't have a repeating structure, and one of the characteristics of vitreous substances, or of the vitreous state, as opposed to the crystalline state, is that vitreous substances don't have a discrete melting point, whereas a crystalline solid, it has a discrete melting point, a point where it transitions to the liquid state. As we can see on this diagram, we have the line going from F1 to L to F3. Along that dark filled in line there, we have a transition from the crystalline state to the liquid state, whereas the vitreous state doesn't have a discrete transition to a liquid state. It just sort of progressively gets softer and softer. So like glass, if you start heating it, it will get softer and more malleable. And then at a certain point, you can say it's liquid, but there's no discrete transition point. There's no melting point in the way that other substances have. And so what this diagram shows is that these transitions of states are they're a function of both temperature and pressure, so that there has to be a combination of the correct pressure and temperature states in order for a particular state of matter to occur. So yeah, the oval here that we have that goes from F1, L, F3, M, N, and then back down to A2, S, A1. So that oval sort of surrounds the crystalline state. Actually, no, sorry. I can't tell where the boundary is supposed to be. I think maybe the crystalline state is just the part with the hash marks up at the top. But each of these curves on here, it represents a boundary between one state and the next. So there's the liquid state. Yeah, I'm not sure what L stands for here. So it says L negative and L positive. I'm not sure what the L is exactly, but yeah, we have a transition from the liquid state to the crystalline state, and then we have a curve from B along that curve, B, and then a dotted line, and then C. That curve is labeled as the curve of vaporization of a vitreous body. So the vitreous bodies will emit a gas from, like, you have a vitreous body, and it emits gas at a certain rate. So it's a certain amount of the vitreous substance will turn into a gas. And then we also have the dark curve from A2S to A1 is labeled curve of sublimation of crystal. So the crystal form, so the crystal state above that line passes directly into a gaseous state below that line. And then the other curve, where is that? Yeah, so the other bit that goes from A1 to C is the curve of vaporization of liquid. So it's the liquid state above the curve passing the state below the curve. I think those are all the labeled curves.
Didn't you say the gaseous is the lower right quadrant, though?
Yeah, so the curve going from A1 to C, we have the liquid state above the curve, and then the gaseous state below it.
But I thought I didn't understand what the thick line, because I thought you were saying the thick line did that as well, but it's sort of on the other side of the gaseous quadrant.
Yeah, so the thick line, so the gaseous quadrant goes all the way along from the bottom right all the way along to so it's really the bottom, I guess, not the bottom right. It goes all the way along to the y-axis. So there's but it transition. There's different transitions. So in the upper right side, we have a transition from liquid to gaseous, and then the thick line from A2S to A1, we have a transition from crystalline substance to the gaseous state, and then from A2 to B, in the single line, we have the vaporization of a vitreous body. So transition from vitreous body to a gaseous state. So there's three different transitions into a gaseous state that are represented along the portions of that curve.
Do we know what the dashed lines are? Because I guess at first I was thinking that the gaseous state is just a quadrant that's kind of delimited by those dashed lines, but now it seems like they seem to be more like guides of some kind than actual. It seems like the gaseous state actually has a different shape. It's not just a quadrant. Am I reading that right?
Yeah, that's my understanding. Is that the dotted lines, I think, are meant to indicate points along the curve. So if we look at the point F1, for example, and then you have the vertical line that proceeds from T, F1, F3, and upwards, and then the horizontal line from P to A to F1. So those dotted lines are pointing out that point F1 and where it's located on the temperature and pressure axes. The other dotted lines, I'm not sure what exactly they're doing. The ones that are inside the oval. So we have delta V minus, delta V plus. So delta normally means change. So change in volume, I suppose. I'm not sure what it is here. Okay, yeah. So yeah, you have a change in volume, which is as you go from a higher pressure to a lower pressure, you have a change of volume. And then you have the L. I'm not sure what the L stands for actually, but there's L negative and L positive is what it says on there.
So I guess what he's doing, I'm just looking at the paragraph. So he's talking about these privileged directions in crystallized substances. And maybe that's what it sounds like with these dashed dotted lines. He's somehow trying to mark those off.
I don't think the dotted lines correspond to the dimensions or the privileged directions within the crystal. But what characterizes the crystalline state as opposed to the vitreous state is the fact that it has those privileged directions, or not all directions within the substance are the same in terms of structure. So you have one structure. If you proceed through the mass of the substance in a certain direction, you have a repeating structure, the crystalline structure. And then if you proceed at a different angle or different direction, then you would not come across that same structure. So there's certain directions within the substance are privileged in that sense.
I see. Okay, so that would be within the crystalline state. So I guess he's talking about another thing. Just in the beginning of that paragraph, there is an evident discontinuity between energy of the macroscopic and the microscopic. So I guess here it seems like there is a discontinuity is going on between the crystalline and the amorphous states. And then we have within the crystalline state, we have these privileged directions, which it sounds like have to do with the crystalline structure itself. And those aren't visible on the diagram, but maybe something about like these crossover points between the different states. I guess that's what we're seeing on the diagram.
Yeah, that's right. So the diagram is in phase space, like you can say. So it shows the different possible states of the substance. So it's not a geometrical diagram in the sense of it's not in geometrical space. But then in the crystal itself, those privileged directions are geometrical. They're in geometrical space. So that those directions aren't shown on the diagram, but the transition from the crystalline state to the vitreous state is shown on that line from the from N down to A2. You have the crystalline state on one side, and then the vitreous state on the other side.
Did we have a thing earlier? Some reason I'm remembering. I don't know if it was this group or not. Maybe another discussion. But the point about water. Water goes it changes state, but it doesn't do it kind of smoothly. It has like a sudden transition at a certain temperature. And and I guess going to show that it's, there are these discontinuities maybe, or these like sort of singular points. That's what that's sort of is resonating. I mean, I know Simondon talks about singular points quite a bit, and uh, maybe that's one of the things we're seeing here.
Yeah, so in the case of water, the ice form is a crystalline structure, as you can see just by even just looking at a snowflake, you can see the crystalline structure with the naked eye, or under a small microscope even, and there's a discrete transition at 0 degrees Celsius. From the liquid state to the crystallized state, and that's at normal atmospheric pressure at sea level, because as the diagram shows, the temperature and pressure are both involved, or both affect the outcome, and then that's what characterizes water or ice as a crystalline substance, whereas with vitreous substances, there's no discrete transition point. So you have just a piece of glass. As you heat it, it will become softer and more liquid-like, and then eventually you can pour it and so on, like a liquid. But if there's no discrete transition point between the liquid state and a solid state.
One thing that helped me understand this section, and really only when I got to the end of it, was to remember that the section that came before this, he was talking about the pendulums and the way that potential energy is converted into kinetic energy and then back, whereas different potential energies are converted into each other without a change in the structure of the system, whereas here, for the potential energy to transform, the structure of the system itself changes.
Right, yeah, that's a helpful reminder of sort of where we are in the argument of the chapter. So he's looking at irreversible transformations. So in the case of the pendulum, it was a reversible transformation of the system, where you have the swinging of the pendulum back and forth. You have a transition from, or you have a transformation from potential energy into kinetic energy, and then back into potential energy as the pendulum swings back and forth. And it's a reversible transformation as long as you abstract away from friction. But in the cases that we're looking at here, these are irreversible transformations of state of matter. So it's or they're not so much irreversible, but to reverse them requires an input of more energy. To take ice and turn it back into water requires an input of more energy. So it's not a reversible transformation in the sense that the pendulum transformation of energy is. Oh, maybe one more point before we move on. So he mentions here the I think it's 32 structures of a crystal. 32 classical groups of crystals. So yeah, the structure of crystals can be represented using groups, the mathematical object, a group, and there are I guess 32. I didn't know the exact number, but there's a certain limited number of possible crystalline structures. So different chemical substances will crystallize in different forms. Like a cube structure is one. Sodium has a cubic structure, but different substances have different crystalline structures, and each of those structures can be modeled as a group. So there's a very direct mathematical description of that structure.
So I'm curious about that point. I'm wondering how he would think that in terms of. So it seems like when we have the crystallization happening, that is an individuation process, right? Like we're kind of witnessing individuation sort of coming into being. Like in the video that was it Angus who posted a little bit further up. So yeah, the sulfur crystallization. Okay, so and it seems like Simondon would say those structures, like the way the crystals form, the geometry of the crystal is somehow maybe there in a pre-individual state, like in a virtual state, before the crystallization happens, when we still have the metastable liquid. Somehow, it seems like there is maybe information about the way the crystal needs to form, because it always forms the same way, right? There's some, as far as I understand, anyway. It seems like those are patterns, right? Certain fixed ways that the crystals form, and I guess in terms of the ontology that he's developing, I guess what we're seeing there is there's some pre-individual information maybe, and maybe certain singular points that are kind of there in a virtual way, and then when the conditions are right, they kind of they actualize.
Yeah, I think that's mostly correct. The only thing I would maybe change is that, as we'll see in a little bit, there are some substances that can crystallize in more than one way. So it's not always the same crystalline structure, and it can so the same solution can crystallize in more than one crystalline structure, and so because of that possibility, I would say that it's not so much that the eventual crystalline structure is sort of virtually present already in the solution, but because in those cases where you have more than one possible crystalline structure, there's a sort of historicity, I guess you could say, to the process of crystallization, because which form will result depends on which form gets introduced into the solution as the germ crystal. It will crystallize in one way if it has a crystal of a certain structure, and crystallize in another way if the germ crystal is of a different structure. And so it's dependent on the history of that individual portion of matter. I think maybe how I would want to express it is that there already is a structure in even in the supersaturated solution before crystallization. It already has a structure of a certain kind, but that structure is transformed by the crystallization and appears at a higher level, a higher order of magnitude. So whereas the solution has only a microscopic structure, the crystal that results has a macroscopic structure. So I think it's a transformation of scale rather than something like a virtual structure that was already present in the solution.
I see. Okay, so I guess part of the point is, I mean, the way I'm thinking about this, it seems like, as far as I know, the geometry is somehow already present on the level of each molecule. Isn't that right? Because of, I suppose, the chemical bonds and just the arrangement of the atoms in a molecule. And then it seems like as the conditions change, molecular geometry kind of gets, I guess, translated, like you're saying, on a macro level, of the solute, like the entire beaker, let's say.
Yeah, I'm not sure exactly what the relationship is between the molecular structure and the crystalline structure. Like if there's some sort of parallelism or something like that between the two. So I wouldn't want to say one way or the other exactly how that works, but the molecular structure at least determines the crystalline structure, or it produces or it limits the possible crystalline structures that can appear in the solution eventually. But yeah, I don't know the exact relationship between the molecular structure and the crystalline structure. But I think we should go on so we don't get sort of bogged down on just this one passage. So if someone else would like to read, starting from the top of 65, the Milky melting characteristic.
The Milky melting characteristic of amorphous solids never shows two distinct phases. Thus, Tamman considers the amorphous solid as a liquid whose rigidity and viscosity have been sufficiently reached due to extremely high temperatures. The theoretical consequences of Tamman's hypothesis are quite important. A liquid that experiences a reduction of temperature without passing to the crystalline state is continually transformed into a vitreous body. It is therefore in a state of supercooling. Experiments on piperine C17H9O3N and Bitol C10H7CO2C6H4OH, which are substances that melt at 128 degrees Celsius and 95 degrees Celsius respectively, and easily remain in supercooling, have confirmed this hypothesis. But the mere consideration of the structures corresponding to the various states is incomplete and leaves behind an indetermination. This consideration must be completed by the study of the different energetic levels linked to each state and of the exchanges of energy that are produced during the state changes. Tamman's theory has an exemplary value because it leads to a study of the correlation between structural changes and energetic changes. In fact, it allows us to determine the conditions and the limits of the stability of crystalline and amorphous states. There are many bodies that can be present in the crystalline state or the amorphous state. Yet, depending on temperature and pressure conditions, sometimes the crystalline state is stable while the amorphous state is metastable, and sometimes vice versa. The passage from the metastable state to the stable state gives rise to a determinate thermal effect and to a determinate volumetric effect. This important consequence of Tamman's theory can be represented by Figure 5. If we begin with a substance in the state of stable equilibrium under a pressure P, and if we progressively lower the temperature by maintaining this constant pressure, the representative points will be displaced from right to left on F1P parallel to the axis of temperatures. If the representative point enters into the domain of stability of the crystalline state, the liquid in question will be in the metastable state. In this state, the supercooled liquid can pass to the crystalline state, and this passage depends on two factors: the power of spontaneous crystallization that this liquid presents, defined by the number of crystalline germs that spontaneously appear in a set time within a given volume of liquid, and on the other hand, the speed of crystallization, i.e. the speed at which a crystalline germ develops.
Right. So the other element of that diagram that we didn't mention is the question of which of these states are stable and which ones are metastable. So that that delta V minus delta V plus was the volumetric effect that he mentioned. Yeah, there we go. Volumetric effect. And then I'm guessing that the L negative, L positive on the other axis is the thermic effect that he mentioned. So some substances will release energy when they release heat when they crystallize, or absorb heat when they crystallize, and so on. There's different thermic effects. which I don't really know enough about in detail. Yeah, so some of the states that are depicted on this diagram are stable, and others are metastable. Okay, I don't really have much to say about that bit, so I think we can go on to the rest of this continuing giant paragraph.
The state of supercooling is easy to bring about if the maxima of these two factors, depending on the temperature, are sufficiently distant from one another, such that one of the factors corresponds to a practically null value of the other factor. At this point, since these two factors both tend towards zero when the temperature continues to decrease, it is possible to cross quite rapidly through region 2, which corresponds to a small but non-null probability of crystallization, and to arrive at region 3, for which the chances of crystallization are practically null. Figure 6. While the liquid is in the metastable state, we can initiate crystallization, which is brought about with an emission of heat. This crystallization makes it possible to measure a latent heat of crystallization, which is the difference between the caloric capacity of the mass considered in the amorphous state and that of the same mass considered in the crystallized state, multiplied by the variation of temperature, dL equals, or delta L equals Ca minus Cc times delta. However, since the specific heat of a substance held in the crystalline state is inferior to the specific heat of this same substance held in the liquid or amorphous state, the latent heat of crystallization varies in the same direction as the temperature. It diminishes when the temperature lowers. Thus, for a sufficient lowering of temperature, what will happen is that the latent heat of crystallization is nullified and then changes sign. The line MS of figure 5 represents the location of the representative points for which the latent heat of crystallization is null, depending on the various values that the pressure, which is constant for the same experiment, can take. Not sure, maybe stop here or take it to the end. Quite a bit.
I think you can go ahead to the end of the page.
Okay. Do you mind stopping me? I don't have the I have a e-reader version, so I don't have the page.
Oh, okay. Sure.
Yeah, even just
I'll let you know where to stop then.
Sure, perfect. Now, let's consider the same liquid substance in the stable state at temperature T, which is in the domain of stability of the liquid state. If the pressure increases, we enter the domain of stability of the crystalline state. Since the liquid is then in the metastable state, the possible crystallization will correspond for each pressure considered with a variation, delta V, of the volume that accompanies this transformation. If Vc and Va are the respective volumes of the considered mass of the substance, whether in the crystallized state or in the amorphous state, then we get the formula d delta V equals dVa minus dVc. If the variation of volume is affected in the direction of a contraction of the plus sign, it will be found that, as in the case of the latent heat of melting, delta V diminishes when the pressure increases, because a substance held in the amorphous state is more compressible than in the crystallized state. For a sufficient increase of pressure, delta V can be nullified and then change sign. The curve Ln of figure 5 is the set of points for which the variation of volume is null. Below this curve, delta V is positive contraction. Above this curve, delta V is negative dilation. From the limits of the variation of the latent heat of crystallization and of the variation of volume, we can deduce the form of the crystallization melting curve. Along this curve, there are two triple points, A1 and A2, for which the crystal, the amorphous body, and the gas could coexist in mutual equilibrium.
Okay, you can stop there. That's great.
Sure.
Thanks. Yeah, so this is still dealing with that same diagram. And yeah, so I was right that the line M to S, that dotted line, and going through the oval region is the region of that thermic effect. It's the line along which the latent heat is null. So where there's no release of heat in crystallization. But then, yeah, so there's also discussion of figure 6. If let me just go back to that for a second. There we go. So yeah, figure 6 shows the 3 regions in relation to temperature. So temperature along the x-axis, and then the y-axis is the capacity of crystallization. And so there's 2 properties that that determine the crystallization. Is the likelihood of a germ forming spontaneously, and then the speed with which the solution will crystallize around a germ. And those 2 properties vary with temperature, but they have their peaks are at different points for this particular substance. So that that means that there's a region which is region 2 in that diagram. There's a region where they overlap, so they aren't at a peak, but there's an overlap, so that there's both a likelihood of the crystalline germ, the crystal germ of forming, and then also a likelihood of or a speed of crystallization around that germ. So it's region 2 is the region where the crystallization process is most likely to happen. Region 3 is the region below it, or in which there's the temperature is too low for crystalline germs to form in the first place, so that the substance is not going to crystallize in that region. If we assign to the variation of volume in the sense of a contraction the plus sign,
in and out, we're thinking maybe.
So meaning that it's essentially arbitrary whether you want to use the plus sign to describe a contraction of volume or a expansion of volume. But in this case, we're going to assign the plus sign to the contraction. Okay, good. Sorry about that. Yeah, so I was just mentioning a translation issue where I think there's a better translation. Hopefully, everyone got that part. It's not a big deal. It's just sort of a one little sentence in passing. Yeah, I don't have much to say about this bit. I don't know if anyone else has any points that. So you didn't hear the translation point. So it was a sentence about 3/4 of the way down on page 66. The sentence, if the variation of volume is affected in the direction of a contraction of the plus sign. So that bit, I think, would be better translated as if we assign the plus sign to the variation of volume in the direction of a contraction. I think that is a better translation and makes sense of that passage better.
I wanted to ask something just about this section, and I mean, I'm really curious exactly what he is doing here in the sense of, so, my first impression is, wow, this reads like a graduate level textbook in, I don't know, physics maybe, or not sure what the field would be exactly. Probably like state, whatever part of physics studies, the states of matter and so on. But he is using it, for a philosophical purpose. And so I'm very curious, like, what exactly is going on? like not, I don't mean just, the specific sort of, um, like what do the different variables mean? What are the relationships? Uh, and, but kind of, um, like maybe on the level of methods, I don't really know even how to ask it. But I guess my thought though is, it seems like what he's doing in passages like these, he is kind of demonstrating this intuition that he's talking about. The way that we can actually sort of penetrate into the process of individuation, this ontogenesis, this like structurations and the various, relations between elements and the way, energy kind of shifts between the disparate domains. It seems like he's kind of enacting that kind of knowledge in passages like these. And so in a way, it reads a lot like phenomenology. There is this descriptive aspect to it, but it's also very material, right? It's very like focused on matter, these material relationships. And so it's really interesting. And I don't think I've really read philosophy like this before. It reminds me of phenomenology. Like I was thinking, Sartre has that famous passage of the waiter in the cafe, right? Pierre. And he gives a lot of description, right? But it's very different. Like it's very different from this kind of like really sort of like really concrete material physical description. And it's yeah, it's really interesting. And I'm just wondering, um, how to make sense of it.
Yeah, I think that's a good question, because you're right that the methodology that he's using here is quite different than, say, a phenomenological one. But so we can compare them in the sense that they're both rely on something like a thick description of whatever phenomenon is being discussed. They're different in the sense that this is a description that relies on scientific knowledge rather than something like lived experience in the case of phenomenology. And I think this comes out of sort of the French epistemology tradition. People like Bachelard, that and Quantiem, I think maybe as well, though I'm less familiar with his work. But it was a tradition within French philosophy that hasn't really sort of translated over into the Anglophone world in the same way as some other French traditions did. But it tended to have this very close relationship with scientific theorization and description. And I think maybe at on the question of methodology, so part of his criticism of the hylomorphic schema was precisely that lack of specificity, the way that it leaves the interaction between form and matter as this dark zone between the two. So in order for that criticism to be, or in order for his theory not to fall victim to that same criticism, he has to have a very detailed account of the of the actual physical processes that he's talking about. So our knowledge of individuation has to be something that that can be very detailed in this physical sense, not just something that is sort of at a level of generality. Yeah, Foucault maybe would be a good comparison as well, because he was also coming out of that epistemology tradition from Bachelard and Canguilhem. So yeah, there's a certain similarity in terms of the very detailed analysis of whatever the subject matter in question is, based on in this case physical theory, but in Foucault's case more in human sciences. So I think maybe another way of putting it would be that the detailed analysis, or the detailed descriptive detailed description of these physical processes serves as a demonstration that we can have a very detailed knowledge of individuation. That our knowledge of individuation is not at the level of a generality like form and matter, but we can actually enter into that process of individuation in our knowledge.
Seems like maybe there's even a some philosophy is supposed to have a kind of, or I guess maybe much philosophy is supposed to have a kind of transformative effect on the reader, right? And I can kind of see that here, like, I mean, you start reading this and you kind of get pulled into this world of like strange processes that, I mean, I've never thought about them before, this particular, and like all these examples are so detailed. It's like really getting pulled into that world of, I guess it's the world of transduction, maybe the world of, that middle ground between form and matter. Like, I think it was Angus who was saying that. And it's interesting how, I think there is that point somewhere about almost like a slogan. I don't know if I'm saying this exactly right, but that the knowledge of individuation is individuation of knowledge. And so in the knowing process, the same kind of change is happening for the knower. So there's this like interlinking between epistemology and ontology. And, and I guess, as we read this, like we're kind of experiencing that change, right? And because it's easy, like for me, it's sometimes easy to just gloss over it and just kind of move through these parts. And I did a lot of that when I was looking at the book on the technical objects. But I'm finding like actually sinking into it has almost like a transformative effect.
Yeah, I think that's a good way of putting it. And I think even at the level of his writing style, like these long sentences with sequences of semicolons, or these long paragraphs of that cover 2-3 pages, they sort of have that transductive structure to them. Like you sort of progressively are transforming your thinking as you proceed through this sequence of semicolons or something like that. So I think, I mean, I don't know to what extent this was deliberate on his part, or if he just sort of developed this style in conjunction with his development of his theory. But I think the two go together, that they correspond to each other, or they match each other. Yeah, I think we can continue from where we left off to the end of the section.
In A, the crystallization melting curve encounters both the crystal's curve of sublimation A2 SA1 and the vitreous body's curve of vaporization A1B. This curve of vaporization extends the liquid's curve of vaporization A1C. Furthermore, for each pressure, there would correspond 2 points of crystallization melting, in which the crystal could coexist either with the liquid or with the vitreous body. For pressure P, for example, these 2 points would be F1 and F2. At temperatures lower than this second point of crystallization, the representative point of the substance would again enter the domain of stability of the amorphous state. At this point, the vitreous state would be a stable state, and the crystalline state would be a metastable state with respect to the vitreous body. Undoubtedly, at these low temperatures, the speeds of transformation would be so low that they would be practically null. But this theoretical reversibility of state and metastable states nevertheless keeps all of its importance. It has not been possible to further provide evidence experimentally for point L of the maximum of the melting temperature or point M of the maximum of the melting pressure, but the experiment has shown that all the melting curves have their concavity turned toward the decreasing temperatures, and that for water and several other substances, this concavity is found starting from the triple point A1 in the portion of the ascending melting curve in the direction of the decreasing temperatures. The interest of Tammann's hypothesis for the study of individuation is to establish the existence of conditions of indifferent equilibrium between two physical states, one of which is amorphous and the other of which is crystalline, i.e. states that are opposed in terms of their structures, the first of which is non-organized and the second of which is organized. The relation between two structural states thus takes on an energetic sense. Indeed, the existence and the position of the triple points are determined based on considerations relative to the latent heat of crystallization and to the variation of volume according to pressure, i.e. to thermodynamic work. The limits of a structural type of domain of stability are determined by energetic considerations. This is why, in order to broach the study of physical individuation, properly speaking, we wanted to define the energetic aspect of the relation between two physical structures. An energetic characteristic is linked to every structure, but inversely, a modification of the structural characteristic of this system can correspond to any modification of the energetic conditions of this system. For a physical system, the fact of having a given structure involves the possession of an energetic determination. This energetic determination can be assimilated to a potential energy, for it only becomes manifest in a transformation of the system. But unlike the potential energies studied above, which are capable of partial and progressive transformations according to an ongoing process, the potential energies linked to a structure can only be transformed and unleashed by a modification of the conditions of stability of the system that contains them. Thus, they are linked to the very existence of the system structure. This is why we shall say that potential energies corresponding to two different structures are of different orders. The only point at which they are continuous with respect to one another is the point at which they are nullified, as in points A1, A2, and F1 and F2 of Figure 5. In the case of a pendulum, on the contrary, where two potential energies bring about a mutual ongoing conversion, as in the Holwick-Leger pendulum, Figure 2, the sum of these two energies and of the kinetic energy remains constant during the course of a transformation. The same thing even applies in the more complex case that Figure 3 represents. That was the double pendulum, I think. Conversely, the state changes undergone by the system forces us to consider a certain energy linked to the structure, an energy which is indeed a potential energy, but which is not capable of an ongoing transformation. For this reason, it cannot be considered suitable for the case of identity or of equality defined above. This energy can only be measured in a state change of the system. While the state remains, it is conflated with the very conditions of stability of this state. This is why we will choose to name those energies that express the limits of stability of a structural state as structural potential energies. These potential energies constitute the real source of the formal conditions of possible geneses.
So I think it was Angus who posted a little while ago about that bit where he explains why go into this discussion of Tammann's hypothesis. And he says here, the interest of the hypothesis for the study of individuation is to establish the existence of conditions of equilibrium that are indifferent between two physical states, et cetera, et cetera. So it's the energetic relationship between different structural states, so that there's a certain energy which is required for the transformation of states from one state to another, and then the next, or that last paragraph, he explains the difference between these types of transformations and the case of the pendulum, or the different pendulum cases that he looked at before. So in those cases, you had a continuous transformation of potential into kinetic energy and back again in the pendulum case. Whereas here we have discrete transitions where energy is released or absorbed through the transformation of structure of the system as a whole. So yeah, there's no continuous transformation as there is in the case of the pendulum. Okay, so I think we can go on to the next section of the chapter. So I can read the first little bit. So the section is individuation and system states, and then the subsection 1 is individuation and crystalline allotropic forms, being and relation. We are attempting to show the validity of the notion of structural potential energy by using it as an instrument for the study of cases in which the notion of physical individuation requires a very delicate usage. And this is because these cases constitute quite a remarkable preparatory example, that of crystalline allotropic forms of the same substance. It will indeed be possible in a similar case to grasp individuation not only at the most primitive level, but also at the level most exempt from any inessential logical inference. If it is possible to determine the characteristics of individuation at this level, these characteristics will be anterior to any idea of substance, since it is a question of the same body, of quality and equidity. And yet, if we take up, for example, the study of the crystallization of sulfur, we shall see that it can exist in the solid state in several allotropic forms, the main two of which are sulfur crystallized in the orthorhombic system, octahedral sulfur, and sulfur crystallized in the monoclinic system, prismatic sulfur. At room temperature, octahedral sulfur is in a stable state. Octahedral crystals of natural sulfur can be found in certain tertiary terrains. The crystals that we prepare remain clear indefinitely. Conversely, the prismatic form is metastable with respect to the octahedral form. A crystal of this form, albeit clear when it has been recently prepared, becomes opaque when it is left to itself. The crystal maintains its external form, but a microscopic examination reveals that fragments into a mosaic of juxtaposed octahedral crystals, which is where the observed opacity comes from. There's a word missing there. The metastable state of prismatic sulfur is called crystalline supercooling. This relation between crystalline, prismatic, and octahedral states exists for temperatures below 95.4 degrees Celsius, but reverses starting from 95.4 degrees Celsius up to 115 degrees Celsius, which is the melting temperature. In this interval, prismatic sulfur is in stable equilibrium, and octahedral sulfur is in metastable equilibrium. Under atmospheric pressure, 95.4 degrees Celsius is the temperature of equilibrium between these two crystalline varieties. With this in mind, it can be asked, what does the individuality of each of these two forms consist in? What ensures the stability of these forms? What makes it so that they can both exist at a determined temperature? When either of these two forms is found in a state of metastability, a crystalline germ is required, i.e. a point of departure for crystallization, so as to help it transform into the other stable form. Everything happens as if metastable equilibrium could only be disrupted by the local deposit of a singularity contained in the crystal germ that can disrupt this metastable equilibrium. Once it has been initiated, the transformation propagates, for the action that is exerted at the start between the crystalline germ and the metastable body is then exerted gradually between the transformed parts and the parts that are not yet transformed. Physicists ordinarily use a word borrowed from the vocabulary of biology to designate the action of depositing a germ. They say that the substance is inseminated with a crystalline germ. A particularly demonstrative experiment consists in placing supercooled sulfur into a U-tube, then inseminating each of the branches of the U-tube with a crystalline germ that is octahedral on one side and prismatic on the other. The sulfur contained in each branch of the tube then crystallizes according to the crystalline system that is determined by the deposited germ. The two allotropic forms of crystallized sulfur are thus in perfect contact in the middle part of the tube. If the temperature is lower than 95.4 degrees Celsius, the sulfur remains transparent, and the branch containing the octahedral sulfur becomes opaque, starting with the line of contact between the two crystalline varieties. Opacity begins to manifest at the contact of these two allotropic varieties, and it gradually propagates to the point of taking over the whole branch containing the prismatic sulfur. Conversely, if the temperature is maintained between 95.4 degrees Celsius and 115 degrees Celsius, the direction of the transformation is inverted. The branch containing prismatic sulfur becomes transparent, and the branch containing octahedral sulfur becomes opaque, starting with the line of contact between the two crystalline. Lastly, at a temperature of 95.4 degrees Celsius, the speed of propagation of these transformations is null. There is thus a temperature at which equilibrium is attained between these two crystalline varieties. From a certain perspective, this experiment entails the creation of a sort of competition for a finite quantity of substance between two systems. For all temperatures other than the temperature of equilibrium, and lower than the melting temperature of octahedral sulfur, one of the forms occupies the whole crystallizable substance, and the other completely disappears. Yeah, if someone has the footnotes and can post them into the chat, that would be very helpful. Thank you. Or if no one has them, I can just try to translate them on the fly. So footnote 5 says, we must note that the formation of new crystals in the interior of the prismatic crystal occurs at a scale much smaller than that of the prismatic crystal. Oh, there you go. That's in there. Never mind. I'll let you post the footnotes. Right. Yeah. Footnote 6, I think, is pretty important. It's his notion of transduction is sort of drawn from this example. So this is like the paradigm case of transduction. Yeah. So as some other people mentioned in the chat, there's this notion of allotropic forms that he uses. So allotropic forms are two different forms of the same chemical substance. So in this case, sulfur can crystallize in two different forms, octahedral sulfur and prismatic sulfur. So two different crystalline structures. And depending on the temperature, one form will be the stable state and the other one will be the metastable state, which means that so at room temperature, octahedral sulfur is the stable state, and prismatic sulfur is the metastable state. So that what that means is that any piece of sulfur, any mass of sulfur that has crystallized in the prismatic form is always susceptible to recrystallization or to transformation into the octahedral form. So the shape of the whole block of crystal will stay the same, but the microstructure will change, so that what was a transparent crystal before becomes opaque because its microstructure has changed, has crystallized in the octahedral form. And then again, that relationship changes above 95.4 degrees Celsius. So that above 95.4 degrees Celsius is the equilibrium temperature. So that at that state, neither one transforms into the other. Neither crystalline form transforms into the other. But then from 95.4 degrees Celsius up to 115 degrees Celsius, the prismatic sulfur is the stable state, and octahedral sulfur is the metastable state. So the octahedral sulfur will transform into prismatic sulfur at that level, at that temperature. And then he gives this example I wonder if there's a video of this somewhere, but where you have a tube shaped in a U shape, and then and it's filled with sulfur, and then one end is you insert a germ crystal into each end. So, and one of them you insert an octahedral crystal, and the other end you insert a prismatic crystal, and then the solution the sulfur, will crystallize in each of those forms in each end of the tube, and then they meet in the middle, and then depending on the temperature, one of the forms will recrystallize the other. Okay, so I think this is maybe a passage where we need to keep reading to the next bit to see why he's bringing up all this stuff in the first place. So we can go on to the next, I guess, page and a half or so, the next big paragraph, if someone else would like to read.
And here we begin to grasp one of the primary and fundamental aspects of physical individuation. Individuation as an operation is not linked to the identity of a matter, but to a state modification. Sulfur conserves its crystalline system only if a singularity is not presented to make the less stable form disappear. To make the less stable form disappear. A substance conserves its individuality when it is in the most stable state proportionate to its own energetic conditions. This state's stability becomes manifest due to the fact that if the energetic conditions remain the same, the state cannot be modified by the introduction of a germ presenting an initiation of a different structure relative to substances that are in a different state. This substance can, on the contrary, provide germs capable of involving a modification of the state of these substances. A stable individuality is thus formed when two conditions are met. A certain structure must correspond to a certain energetic state of the system, but this structure is not directly produced by the energetic state alone, for it is distinct from the latter. The initiation of structuration is critical. Most often in crystallization germs are deposited from the exterior. Thus, there is a historical aspect to the manifestation of a structure in a substance, insofar as the structural germ must appear. Pure energetic determinism does not suffice for a substance to attain its state of stability. The beginning of structuring individuation is an event for the system in a metastable state. Thus, in general, even in the simplest process of individuation, a relation takes place between the body under consideration and the temporal existence of beings external to it that intervene as the evental conditions of its structuration. The constituted individual holds within it the synthesis of energetic and material conditions and of an informational condition, which is generally not immanent.
Yeah, so here, again, this whole chapter that we're reading is on physical individuation, and what makes physical individuation distinct is, what distinguishes physical individuation is this relationship between the structure and the energetic system. So that crystallization is the sort of paradigm case of physical individuation, and this is an example that he comes to sort of get away from the hylomorphic schema. It's that relationship between the energetic conditions and then the event of structuration, that historical aspect that I mentioned earlier on. So there's an eventual or historical aspect to individuation. It's always this precise individuation of this entity. It's not something that is purely determined by the energetic conditions of the system.
I'm trying to figure out what he means by the third condition. Like at the very end of what we read, if the encounter between these three conditions has not taken place. And because it seemed earlier that there were two, right? There is the energetic condition and then which seems to be constitutive of this of the metastable solution, and then there is the germ, which is the informational condition. And I guess I'm trying to sort of piece out what the third one is.
Well, in the sentence just before that, he seems to distinguish. So he says, the constituted individual holds within it the synthesis of energetic and material conditions and of an informational condition, which is generally not immanent. So it seems like energetic is one, material is the other, and then informational condition is the third. So those are the three. So energetic conditions and material conditions are distinct. Those are two separate conditions. So what I assume that means, or how I understand it, is you have the whatever the substance is, so sulfur in this case, and then you have the energetic conditions, so the temperature at which the whole system containing the sulfur is at. And then the informational condition is the germ introduced into the supersaturated or the supercooled sulfur. So yeah, those are the three conditions that have to meet for a process of physical individuation to occur.
So I guess the energetic and the material are both immanent, it seems, to the system that's individuating. And then the informational is what's supplied from outside. Generally not immanent. I guess that's how I'm taking that.
Yeah, I think that's right. So he does point. He points out a couple pages earlier that within the supercooled system, you do have the formation of the spontaneous formation of these germ crystals. So they can the informational condition can be immanent in that sense in that particular case, but that's not the general case. So in general, it's not immanent. It appears from outside through the introduction of a germ crystal. Okay, so let's go on from the top of 71. If the encounter between these three conditions.
If the encounter between these three conditions has not taken place, the substance has not attained its stable state. It then remains in a metastable state. However, let's note that this genetic definition of individuation through the encounter of the three necessary conditions leads to the notion of the hierarchical relativity of states of individuation. Indeed, when there is a very large hiatus between the energetic state of a substance and its structural state, for example, sulfur in the state of supercooling, if a structural germ is presented, it can involve a change of the substance's structural state without, however, leading it to its state of absolute stability. If at a temperature of 90 degrees Celsius, supercooled sulfur receives a prismatic germ, its structural state changes and it becomes crystallized sulfur in the prismatic system. It has passed a stable state to a second metastable state. The second state is more stable than the first, but if a second structural germ intervenes, i.e., a crystal of octahedral sulfur, the structural state still changes and the whole mass becomes octahedral sulfur. In this sense, we understand why crystalline supercooling constitutes a less precarious state than liquid supercooling. A structural germ has already been encountered, but it has deposited a structure that is incapable of absorbing into the structuration all the potential energy represented by the state of supercooling. Complete individuation is the individuation that corresponds to a full deployment of the energy contained in the system before structuration. It leads to a stable state. Conversely, incomplete individuation is that which corresponds to a structuration that has not absorbed all the potential energy of the initial non-structured state. It leads to a state that is still metastable. For the same substance, there are as many possible types of structures as there are hierarchical levels of metastability. For example, in phosphorus, we encounter 3 levels of metastability. Furthermore, it is important to note that the levels of individuation are perfectly discontinuous with respect to one another. The existence of energetic conditions of equilibrium between 2 levels immediately following one another in the hierarchical scale can neither obscure the structural discontinuity of these 2 levels nor their energetic discontinuity. Thus, going back to the example of sulfur, when octahedral sulfur is brought to 95.4 degrees Celsius under atmospheric pressure, it is necessary to provide 2.5 calories per gram in order for it to transform into prismatic sulfur. Consequently, there is a specific latent heat of transformation of octahedral sulfur into prismatic sulfur. This energetic discontinuity is also discovered by the fact that the melting point of the metastable variety is always lower than that of the more stable variety for all chemical types. So that sounds like non-manifest's point earlier about there's reversibility, but it requires this input of energy in order for it to be reversible, unlike the pendulums.
Yeah, and the pendulum case is a sort of idealization, of course, because in real life you always have friction. So what in theory is a reversible transformation of kinetic energy into potential energy and vice versa. In theory, that's reversible, but in practice, in real life, there's always friction. So some of the energy is transformed into heat, which means that you can't actually fully reverse the process without an input of more energy. But in this case, so you have the 2 forms of crystal in equilibrium at 95.4 Celsius, and then in order to transform one into the other, you have to add more energy. This 2.5 calories per gram. So there's this specific latent heat of transformation. There's this energetic discontinuity between the two forms. So even though they're in equilibrium, there's still a discontinuity between them.
One thing I find interesting is this interplay between the continuous and the discontinuous. So I guess my impression of, when he discusses the pre-individual, the field, I guess whenever I hear field, I think continuity, right? I think that's kind of natural, sort of like a fluid, right? That's has gradients, but doesn't have, jumps and leaps. But it seems like this continuity actually plays a really important role for him as well. And I'm really curious about, because I think it's a sort of, it's a big kind of question, like how do those two things relate, right? I think you have a issue like that in physics with fields and waves versus particles. So there's this moment like how can we even get a discontinuity within the field of the pre-individual, let's say, or within a metastable field? And I guess maybe part of it for Simondon has to do with these singular points that he discusses. I don't know actually if he's talked about it here, but it's a theme in the other book. And so, I mean, I don't want to jump the gun on, maybe he'll get into that later, but it's interesting because it's coming up here, this bit about discontinuity.
Yeah, I think here the discontinuity is it's a different kind of discontinuity. So it's a discontinuity of the different levels of individuation. So within physical individuation, the system can individuate at different levels, and it's those levels of individuation that are discontinuous with each other. and so the different levels are distinguished insofar as their one is more stable than another, so that one system can pass into the other, one state of the system can pass into the other with a release of energy, and so it's those states of the system that are discontinuous, whereas the singularities that he talks about, I think that has to do with the historical aspect of individuation in physical systems that he mentioned a little while ago. So it's the way that a physical system, which state the physical system will take on, is dependent on that informational condition that germ introduced from outside that brings about the transformation of state in the system. So whether or not it will, so out of those discontinuous states that are possible for the system, the singularity or that informational condition will determine which one gets actualized in that system. So that's the sort of historical aspect. That's where the singularities come in. Okay, I think we have time for one more of these big paragraphs, or one page, I guess, because it's longer than one page. So let's do one more page if someone else can read from the top of 72.
Therefore, it would seem that it is possible for there to be several levels of individuation underway throughout the ongoing changes of the allotropic forms of an element. Only one of them corresponds to a complete individuation. There are a finite number of these states, and they are discontinuous with respect to one another, both due to their energetic conditions and their structures. The effective existence of an individualized state results from the fact that two independent conditions are achieved simultaneously: an energetic and material condition resulting from an actual state of the system, and an evental condition, which most often involves a relation to a series of events that arise from other systems. In this sense, the individuation of an allotropic form begins with a historical type of singularity. Two flows of volcanic lava of the same chemical composition can each be at different points of crystallization. These are local singularities of the eruption that are translated through the particular genesis of this crystallization into the individuation of the allotropic form involved. In light of this, all the characteristics for a substance that result from this double, energetic and historical, conditioning are part of its individuality. Due to the studies of physical chemistry, the geologist knows, based on the history of rocks, how to interpret the relative size of the crystals that constitute them. A paste that seems amorphous but is finely crystallized indicates a rapid cooling of the substance. Large crystals, of which only the external form remains, and whose entire matter is divided into microscopic crystals of another system, indicate that there have been successive crystallizations, the first form having become metastable with respect to the second. From the simple point of view of allotropic forms, an examination of metamorphic rocks is also fruitful for learning about the historical and energetic conditions of geological phenomena, like that of magma, whose source is eruptive. Kalkschist, quartzite, schist, gneiss, mica, schist correspond fragment by fragment to a certain particular modality of endometamorphism or exometamorphism for a determined pressure, temperature, and degree of humidity. Thus, we see that the consideration of the energetic conditions, the singularities in the genesis of a physical individual, does not in any way lead to recognizing mere types instead of individuals. On the contrary, it explains within the limits of a domain how the infinity of the particular values assumed by the magnitudes that express these conditions can lead to an infinity of different results. For example, the dimension of crystals for the same structure. Without borrowing anything from the domain of biology and without accepting the notions of common genus and specific difference, which would be too metaphorical, it is possible based on the discontinuities of conditions to define types that correspond to domains of stability or metastability. Then, within these types, it is possible to define particular beings that differ from one another based on that which, within the limits of the type, is capable of a finer, sometimes continuous variation, like the speed of cooling.
Okay, yeah, you can stop there. Thanks. So here we have, as Alyosha mentioned in the chat, here he seems to group the energetic and material conditions on one side, and then count them as one condition, and then put the informational or eventual condition on the other side. So in a previous paragraph, he listed three conditions with energetic and material listed as separate conditions, but here he sort of counts them together. So I guess it doesn't seem like it's that important whether you count this as three conditions or two conditions for him. It's what the key difference is the one between the eventual or informational condition and the other two. That's the one that really is important to him. And yeah, I think Alyosha, I think you're right that the this image of the volcanic lava and its cooling and crystallization and its historicity, I think that's a better image of physical individuation. And that's the type of image that he wants us to go towards, rather than the brick as like the sort of paradigm example. And in particular, this singularity or the historicity of the transformation process is what allows us to get beyond species and genus type of understanding. And this is something that he criticizes as well in the other book, the Technical Objects book. And in general, he's very critical of species and genus types of approaches to understanding individuation, which would go along with the hylomorphic schema, because the form corresponds to the genus, and then there's a specific difference. But yeah, so here we have we can classify different types of stone or rock based on their characteristics, but that's just sort of a shorthand for a historical process through which those different characteristics came to be realized, where you have a process of crystallization and then a recrystallization in a different form, for example, that we can observe in the structure of the rock, so that the individuation is always historical. I think is one of the key takeaways of this section that we read today. It always involves the particularity of the individuation history process, is part of what constitutes an individual in a physical individual.
To be brief, I think like what we have discussed so far is like a hello, can you hear me?
Yes, now I can hear you.
Yeah. So all different, all kind of beings have different process individuations according to the singularity. Like, and then what Simondong is trying to has been trying to is like to bring some kind of a specify the particular elements to make us understood. So the point is that while reading generalization, categorization, genealogy of beings, like if you think of Foucault like a genealogy or categorization is like meaningless in a way. The point is that every being has its own point of a singularity.
Yeah, I wonder if we can compare this to the genealogical method, because that is also, if I remember correctly, the genealogical method also has to do with a criticism of classification by species and genus, and it sort of points to that singularity of a concept that has its historicity to it. So yeah, I think we can make some sort of comparison with that as well. But I noticed that we're just at time now, so I think we should wrap it up here. And yeah, so thank you everyone for participating, and I'll see you all next week.